So here we are back at Pro Prof quizzes, and we're going to have another look at a multi-choice question paper. This one is by Boilermaker_74. It's 30 questions and has been just short of 12,000 attempts of this since 19th of January 2024. So let's see how we get on with it. So first one here, select the correct MMA welding rod. So we're being given an AWS classification covered electrode. So we've got 7014 electrode here. We do have a video on identification of electrodes on our channel, so make sure you have a check of that. But what we've got here is this is 70,000 PSI. It's all positional, and it's a rutile type electrode. That's 13 and 14. So we can have a look at these answers and go, we've got basic and cellulosic. It's not them. Cellulosic is a 10 and 11, and the basics tend to be 16, 17, 18, potentially 15. And let's look at, so now we're back to these two, which is rutile high recovery or a rutile. A 13 is rutile, and a 14 is rutile high recovery. Great. So we've got that. Right, next one. When weld metal refinement takes place in a multi-run deposit, it is best known by the term. So this is weld refining or grain refining. I kind of remember doing a question like this in the past, and they use the term weld refinement, but really it should be grain refinement. That's where we're reheating the past structure, weld metal heat affected zone, back potentially through the critical transformation temperature, reordering everything, and then letting it cool down again. And that repeated heating and cooling has some potentially good or positive benefits. But it could be bad in some materials, so it depends, really. Next one. Question 3. The most common type of defect found in a structure when it is undergoing service is, so in service, which is the most popular or most common in-service defect. So we've got probably fatigue cracking out of them. Weld decay is in stainless steels. It's reduction in chrome content. Stress fractures. It's a type of servicey thing. I'd like to see what type of stress fracture would be. Maybe if it was real. Crystallization, not really a thing. So let's go with fatigue cracking. There we go. Question 4. Bend test specimens have been taken from 25mm thick carbon steel butt weld, which would show a lack of interrun fusion. So, very common question, and we've seen this lots of times in some of the papers we've already done, that the magic number here is 12mm. So if we're below 12mm, we'll do 2 face and 2 root bends, and above 12mm we'll do 4 side bends. So this is 25mm thick, so we'll go with our side bends. Sulfur and phosphorus are not alloying elements. They are what? It says type here, but what am I meant to type in? Well, here's a guess. So sulfur and phosphorus are non-desired. They generally cause us issue during welding or fabrication. So sulfur creates what we call hot shortness or solidification cracking or hot cracking. It's cracking immediately behind the weld pool as we're welding, very commonly described as part of the submerged arc welding process. Phosphorus is cold shortness, or cold shortness is probably the best word for it. It's cracking when we form materials, so when we bend them, say through 90 degrees in a press brake, something that's got a high phosphorus content or a higher phosphorus content is more likely to crack during that. Should we say impurities? I don't know, and I cannot spell for toffee, so yeah, we'll go impurities and we'll see if that's what they're gonna guess the word they're looking for. There you go. Cool. When you ask a question like that, sometimes it's best at least to give someone a rough idea what type of words they're looking at using. But yeah, we got that right. An IZOD impact test machine will give an indication of a material. This is a funny one because IZODs are mentioned in C-SWIP, I think, once as a passing slide, and I've never seen anything further on them, whether they be in practice tests or within exams at all. Even though I can't directly speak for exams, but in my knowledge, I haven't seen any. So have a think. I'm trying to do this together, even though you can't answer me here. In the comments below, at this point, pause the video, type in what you think the answer of this should be, right? And then we can go from there. I'll click ductility and see if you agree with me or not. Which of the following coatings is associated with stove welding? So this is which of the following coatings in a covered electrode is associated with stove welding. So here we've got basic, rutile, oxidizing or cellulosic. Well, stove welding is the American term for overland pipelines, and it's generally done, well, it's done vertically down. And for that, we need an electrode that's going to burn really hot, because in traveling down in the PG position, we're going to need to generate more heat because we're traveling relatively quick. If we don't generate more heat, then we'll likely get lack of fusion defects. So the cellulose powder that's in cellulosic electrodes, when it burns, it produces a hydrogen shielding gas, which imports more energy over the arc, makes the arc hotter. So it'll be cellulosic. Okay, drone symbol question. You can make these more complicated in your head than what they should be. Work through them step by step. Okay, so which of the following symbols from EN 22553 would indicate a weld has to be flushed on the other side of the weld? So with weld symbols, we always have an arrow line and then our reference line. Within EN, the other side is the dotted line. Okay, so we can get rid of B because B is incorrect. It's only got one line, it hasn't got a dotted line. Now that is potentially possible within EN 22553 if both sides are the same, because it doesn't matter if it's other or our side. So you know that's wrong, but could be American. That would be the other side in the American, but we're being asked for European. So the best answer there, looking down it, is A, because we've got a double V butt weld, and then on the other side, on the dotted line, we've got a weld being flushed. Number 9. If pipe bores are not matched correctly, they can result in when you look, I don't see the correct answer here. I'm guessing it's going to be lack of root penetration, judging on what's here. but it's more likely to be lack of root fusion. So missing one side rather than missing both. Missing both sides and root penetration and not getting any material through is likely because of fast travel speed, low amperage, all them type of things. A lack of root fusion comes from the material being physically stepped out, which will happen when you have the bores of the pipe not set correctly. So the correct answer is lack of root fusion, but the best one out of all of these is lack of root pen, which, so yeah. Fatigue testing is used to test welds under cyclic load, and fatigue is cyclic. So we'll go cyclic there. Pardon me. Question 11, the unit of joules would be used to measure tensile strength. So that's false. Joules is used, it's an energy, so it's used for impact energy in Sharpie V-notch, CVN testing. Tensile tests to EN are in newtons a millimetre squared. Which of the following elements has a greater effect on hardenability of a steel plate? So the greatest effect is carbon. Chrome has an effect and moly has an effect, but much reduced. Sulfur is a hot shortness. Which physical test is more likely to reveal heat-affected zone and embrittlement? This is a funny one. Heat-affected zone and embrittlement. I can see in my mind lots of different reasons why some of these would show it. An all-weld tensile test will know because there's no heat-affected zone in that. Okay, transverse tensile test, if the tensile test fails in the heat-affected zone and it shows a brittle fracture face, so no deformation, crystalline brittleness, so potentially. A root bend could be if you bend it through whatever degree, 90 or to 180, and it snaps in the heat affected zone. That would show heat affected zone embrittlement. And a Sharpie test would show embrittlement because you would have a lower impact energy. What that is showing, in my mind, is a lower amount of toughness, which I guess you can pull into the brittle side of the transition curve. I think the best one there, even though I would, like I say, I would argue with freedom would show it to some degree, more likely I would go Sharpie impact. Just because you're going to be testing in the heat affected zone. So you'd be able to guarantee you would see it or not see it in that area. Whether you have two, it would depend if it failed in that place. Okay, cool. Got that right. My logic's standing up for something at the very least. If a welder is found to be working outside the parameters of a procedure, the welding inspector is within his rights to revoke his approval. So the revocation sections of, say, 9606 are to do with if you doubt the skill of the welder, basically. If he's working outside the parameters, I would say, yeah, you could say that he doesn't understand the WPS, therefore he needs to be retrained. Which welding process is it possible to change from constant voltage to constant current? So this is your flat characteristic and your drooping characteristic. Some processes use one uses both. So we've got TIG welding using drooping characteristic, constant current. MAG welding using constant voltage. MMA using constant current. And then submerged arc changes. It has constant voltage before 1000 amps and then constant current after 1000 amps. So we can use that. Proof stress is used when non-ferrous materials are undergoing tensile tests to determine an equivalent yield strength. That's true. So what happens is we, because there's no defined yield point, we come out a set value on the x-axis. Depends on the standard you're using. It could be 0.2 or 0.5 normally. And then you draw a parallel line up with the elastic section of the curve and plot out its yield strength. You have a macro section on a T-butt joint that shows a step-like defect lying outside the visible has. What would this defect possibly signify? Say it right. So, okay, reread that. So we have a macro section. So we have a photograph of our cross section. We have an indication which is outside of the heat affected zone. So it's not heat affected zone cracking. It's not toe cracking because it's outside of the thing. And this is a step-like defect. So welding has already happened. Then in the cooling phase, likely what's happened is the weld's cooled and it's contracted. It's put force onto the cross-section of the plate. There was some laminations in place, and with the application of force, they've connected up through their stress razors and produced laminar tearing. DWSI, so a double wall single image, is a form of radiographic testing. Well, that's true. So we're going through two walls and only getting one image to look at. So it's a pipe type thing. Which of the following defects would you expect to find by visually inspecting of welds? So what we're going to see from the outside. Well, not, sorry. Reread the question, James. Come on, I'll read it properly. So we'll start again. Which of the following defects would you not expect to find by visual inspection of welds? So undercut we can, linear misalignment we can, linear slag inclusions we can, overlap we cannot. It's always interesting when I teach welders the course. They go, well, of course you can see overlap. You can potentially see areas where it looks cold, where it's got a bad transition to the base material, but overlap is the point that comes back in along the connecting point between the weld and the plate. So there's this slot of welds. I'll try to remember to put a little drawing up somewhere of what that looks like. And that we can't see and can't measure in visual inspection because it's an internal defect, or it acts like an internal defect. Now, my answer is right. Linear slag inclusions, of course you can find them. Yeah, see them all the time. See them on the plates in your inspection results. So, yeah. Spatter may be finely controlled during MIG-MAG welding by So spatter is controlled by the use of inductance. So have we got it? Yeah, adjusting inductance. So inductance, or another word for it, is welder choke, and it's where we reduce the peak current during the short circuit side of dip transfer. So as the wire comes down and makes contact with the plate material, we get a short circuit. That generally pushes a high amount of amperage through the system because it's a short circuit. When the wire then snaps, it generates a lot of force, which throws a lot of spatter out of the weld arc. So by stopping that peak, which we don't need, by using inductance, we reduce the amount of spatter. Which gas shroud should be used when tungsten arc gas shielded welding aluminium alloys? So which shroud should be used when TIG welding aluminium? I'm just trying to make better sense. Which gas should be used when we weld aluminium? Is with TIG, is what the question's asking. So we use argon in doing that. Yeah, TIG doesn't do well with a carbon dioxide in it at all. The electrode tends to react violently. Nitrogen, we use a small amount of it when we're doing things like super duplex. It's an austenite promoter. So, a tough laminated structure that is formed on slow cooling of ferrite and iron carbide ceramite is called, it's perlite. That's a fairly detailed question for a C-SWIP examination, right? I'd be very surprised if you do that because we don't actually teach it. But perlite's the structure we want to find. Martensite is fast cooling from the critical transformation temperature. Austenite is what it is above the critical temperature. So in carbon steel, above 723 degrees, it's austenite. Manual metal arc electrodes stripped of the flux. That's this question again. It's like it exists in a homework question in the C-SWIP 3.1 for years, and it has just been regurgitated in every practice exam anybody has ever decided to use. But here it is. It's if you use MMA electrodes and you strip the flux, you get the wrong chemical composition because the core wire within the MMA electrode is cheap garbage. You know, it's carbon steel, it's reaming steel. It needs the flux to alloy and increase its quality. So if you remove all that, it's just garbage. So the composition will be wrong. Okay, a welder qualification test is to verify skill of the welder, yes. The quality of the materials, nope. The manufacturing methods, no. That's a weld procedure test. A non-destructive test procedure, nope. So skill of the welder. Welder qualification tests are designed to, these are random, so I guess we've just had something similar come up one after the other. It's all about the same though, isn't it? The correctness of the welding procedure, the test of welder skill. It's test of welder skill. A welding qualification procedure, so a WPQR is used to test the correctness of the welding procedure. A welder qualification test is to test the skill of the welder. No. I'm reading his justification here. So a welder qualification tests are designed to test the correctness of a welding procedure. No, they're not. A procedure qualification test is used to, I guess maybe it's just they're using the wrong term here. Yeah, I think if you changed the question and said a procedure qualification tests are designed to, it would be test the correctness of the weld procedure and prove the weldability of the materials, but not to test the welder skill. You can get it, but it's not for that. So yeah, just bad question. Obviously, it's mixed up in a couple of other things, so we'll ignore that one. Okay, another one. Well, we've got to type our answers in, so we'll guess the word. Quenching a carbon or low alloy steel will result in an increase in hardness and a reduction in ductility. So increase, how do you do this? Do you have to put a comma between them? Reduction. Should we try that and see what happens? Oh, decrease. See, if you don't know the word you're looking for, you can't. So I went reduction instead of decrease. Maybe I should have kept them the same because I said increase, decrease. Would have been sensible, but they're the same word. So I'm going to say I got that right. Then we go for it. Quenching a carbon or low alloy steel will result in an increase in hardness because it's more likely to promote martensite, and a reduction in ductility because if it's hard, it's not ductile. They kind of don't go together. Yeah, so that's that. The property of a metal to return to its original shape is called elasticity. Elasticity. Yeah, again, I cannot spell for life. Thank God for spell check. Okay, so we can pull it to a point, we let go of it, it'll return to its original size. That's where we want to be in fabrication, because if you go past the elastic point, you get deformation, you get yielding, and your bridge will get longer, your building will change shape, and all that type of thing. It's not what we want. A steel composition in a structural contract is changed from 0.15% carbon, 0.6% manganese to 0.2 carbon and 1.2 manganese. Might this influence the incidence of, well, what are we doing? We're increasing carbon, we're increasing manganese. So instantly our CEV, our carbon equivalent value, is going to go up. Therefore, we're at a higher risk of cracking. So we'd need to do something to potentially to combat that. More preheat, longer cooling down rates tend to be the two big ones. So I'm going to say cracking in the welds. It's going to increase the chance of cracking. Laminar tearing has... Okay, let's see if we get this one right this time. So laminar tearing has occurred in a steel fabrication. Before welding, could it have been found by dye penetrant? No. It's no. X-ray? No. Ultrasonics? No. It couldn't have been found by any inspection method because laminar tearing is the effect, is the process of producing cracks between laminations. If we had UT'd the material beforehand, we find the laminations, and we can potentially do a straw test, a short transverse reduction in area, to understand what the risk of the through thickness ductility is. So it couldn't have been found beforehand. Get in. This person got it right. We have seen people get this wrong in the past, but this one is right, so this is good. I'll just say on that though, people need to just give up on that question, right? It was a stupid question just to catch people out back in the day, and it's sort of fed into the I don't know what word I'm looking for, into the everything that happens, right? So, okay, so I've got a picture now. Select the correct welding process. So this is TIG. We've got a filler wire. We've got a tungsten here. Our tungsten is producing an arc across the gap into the weld pool and heating it and making the weld pool there. We've got a shielding gas, normally argon. And then we've got the torch and our ceramic and all that type of thing. So that would be TIG. Okay, so that is the next set of 30 we've done. I didn't get them all right, but I think we can see why at least I disagree with the answer. Great to hear if you disagree with them as well, or you think I'm wrong. I'm happy for people to say, no, James, you completely read that wrong. You're an idiot. So again, drop in the comments below. If you're not already a subscriber, come on, hit the button. It's free. It's not going to hurt you. Just hit it, watch some more videos, and we're good. And we'll be able to produce more videos like this and help people learn as much as we can. So with that, then, thanks very much for your time. I hope everything goes well, and good luck with your studies.